I'm so sorry. Yeah, that's fantastic. I've got it in progress. Mark, over to you. Thank you.
Ben, that's really great. Just sorting something out there. So firstly, thanks very much to Jeanette and VfCA for having me here. And before I start, I'd just like to acknowledge the traditional owners of the lands on whom I'm standing today. That's the Ngunnawal people, and pay my respects to the elders past and present. In language on country, it's Darawa Nuna, Darawa Ngunnawal. So I just want to probably kick off my presentation in a second, just to sort of cover this. So just checking, there's a full screen there for you. All good, fantastic. So what I've been asked to do is give a quick sort of coverage of what's an incredibly complex and data-rich area. And so to put this in sort of context, the last IPCC reports were around about 12,000 pages of densely packed text with something like over 100,000 references therein. And so this is, a huge condensation of a lot of information, some of which I'll be drawing from IPCC and also from other sources. So tonight I'll be talking about what's happening to our climate in terms of climate change, some of the things that may be impacting on animals in different circumstances, and also their carers, and also some adaptive responses. So the things that we can do about this, and even a little bit about the greenhouse gas emissions that Jeff just talked about just before. So when we look at the core issue of climate change, it's actually huge amounts of fossil fuels which have been dug up from underground or outgassed from underground in the case of gas, and put into the atmosphere. And so we're building up the atmospheric carbon dioxide levels at a huge rate because we're actually emitting billions of tons of carbon dioxide from these sources every year. So this graph shows the carbon dioxide just from the fossil fuel, that's the coal-fired power stations and similar things, and industry sources, think cement manufacture. And we can see that just from these sources, we're about 37.5 billion tonnes, whereas going back 1990, we're around 22 billion tonnes. So we've increased the amount of these emissions hugely in that time frame. And even events such as the global financial crisis or the COVID pandemic drove down emissions, but very temporarily. Within about a year, they were back up and above where they were previously. And so unfortunately, the last couple of years, we've again had record levels of carbon dioxide emissions, and that drives up carbon dioxide concentrations in the atmosphere because carbon dioxide is a very long-lived gas, and it hangs around for hundreds to thousands of years. So it accumulates in the atmosphere. When we add the other greenhouse gases and the carbon dioxide from land use clearing, we're well over 50 billion tonnes a year of greenhouse gas equivalents, which are being emitted. And so that's piling up in the atmosphere. So we have record levels of methane, record levels of nitrous oxide in the atmosphere. And we've known for a couple of hundred years now that if we put those greenhouse gases in the atmosphere, we'll warm the Earth. So this is not new science. It was actually first worked out in the 1800s. And the first models of this, the most modern models of this were done in the 1970s. So we've got a long heritage of understanding of how greenhouse gas accumulation in the atmosphere will change temperatures across the globe. So when we look at what's actually happened to our temperatures, this record goes back to 1850. Separate set of records, so 6 different sources, but they all show the same picture, which is our globe is warming. This is a global temperature average. You can see there still remains variation around the long-term trend. So that's amongst other things caused by El Nino and La Nina years. Volcanic activity can usually cool the world, but in the most recent, that big explosion in Tonga, that actually warmed the world. And so you get multiple sources of variation that cause the little ups and downs around the long-term trend. When we look at what's likely to happen this year, we're likely to get record temperatures again either this year or next because of the emerging El Nino in the Pacific. So El Ninos tend to boost temperature up by around about 0.2 degrees, and La Ninas tend to drop it down by between 0.1 and 0.2 degrees. So we're likely to see this records that we have recently be broken again. And so our temperatures are likely to continue to go up. These temperatures and related changes, so related changes to rainfall and sea level rise, are already generating impacts right across the globe. This is a map from the IPCC, which shows those areas where there's studies and evidence of climate change impacts to date. And you can see that there's no continent, no island, no ocean, which is not affected by climate change. And that's what's happening now in like the 2020s at around about 1.2 degrees Celsius of warming above pre-industrial. And unfortunately, we're heading closer at the moment. Our trajectory, as I'll talk about later, is close to 3 degrees. So one can, start to get a picture of how dramatically the world might be changed if we keep on going our merry way in terms of greenhouse gas emissions. So when we look at what's important in terms of animals of different types and also their carers, it's not so much the average temperature, which those previous graph showed, but it's actually the variation in temperature, the extreme temperatures, both the extreme hot and the extreme cold, which drive a lot of the negative impacts in terms of animals. So when we look in this particular case, it's the area of Australia, which is experiencing what used to be thought of as a very hot year. So if we look at the long-term temperatures, we select out the hottest 10% of years. That's what's called the 10th decile of temperature. And then we map those areas in Australia which are experiencing for that place a really hot year, one of those 10th decile years. And you can see if we go back, say, Second World War type timeframes, very little of Australia was experiencing what you'd think of as a very hot year. But these days, the long-term trend, that black line there, which is the 10-year rolling average, is around about 60% of Australia is experiencing in any given year what used to be thought of as an extremely hot year. So these are the types of years where animals and humans get heat stress and with all the negative health and reproductive implications that brings. You can see the most two recent years in this graph actually much, much lower than that trend line. That's the influence of La Nina on our climate. So when we get a La Nina, we tend to get more rainfall. That tends to cool the continent, and I'll talk about that in a second as well. So we can see, though, that that coverage of extreme conditions is in itself extreme. It's quite extraordinary that we're seeing that proportion of Australia experiencing those conditions in any given year at just 1.2 degrees average rise. Now, if we look also at rainfall, because that's really important in terms of agriculture, important in terms of the environment that animals and their carers experience, we've also seen a drying of southern Australia, particularly in autumn, winter, and spring. And so in the Murray Basin, which is our most important agricultural catchment, we've already seen about a 40% reduction in river flows compared with the long-term average. And a lot of that's driven by climate change, not quite all. And I'll show you, and I think I'll show you later what might happen in the future. But we're already seeing big changes, and they're likely to increase in the future. And so water allocations to environmental flows and hence biodiversity and the animals that rely on water flows, environmental flows in our rivers are going to become more challenged under climate change. Now, what I'll show you in the next few slides is a little bit to sort of indicate the sort of scale of change in our operating environment that we've seen already in terms of climate change. So what I've done here is a really simple thing. I've plotted for each year. So each dot on this graph is a different year. And I've taken from the Bureau of Meteorology the rainfall and maximum temperature of that year and plotted it on this graph. Then I've drawn a straight line. That's a line of best fit, so a statistical line, just a regression line. and then drawn a hand-drawn ellipse around that. So that's essentially the envelope of variation, if you want to think of it like that. Now we can see that there's actually a really strong relationship in there. Those years which are wetter are also colder. Those years which are drier are also hotter. And the physical explanation is very straightforward, is that if we have a wet year, we've got more cloud cover over our continent. That cloud reflects sunlight before it ever reaches the Earth. And so the Earth is cooler because it doesn't get that sunlight warming up the surface. We've also got a lot of water on our landscape. And that water, when it evaporates, absorbs a lot of energy, just like sweat on your skin absorbs a lot of energy when it evaporates and you feel cool. A lot of water on our landscape keeps our landscape cool. And so those years which are wetter, for very straightforward reasons, physical reasons, are also colder, and vice versa. So if we look at those years between 1950 and 2000, and also those years post-2000, we can see exactly the same relationship. So the slope of that line, the regression line, is almost identical across those three different periods. So in other words, the same physics of cooling or heating is working in all three different periods. And it's only though when we actually overlay these, which we actually see the degree of change that we've experienced already. So if you look at those hand-drawn ellipses, the most recent period, post-2000, almost has no overlap now with the pre-1950s period. So we're almost in unprecedented territory already when it comes to climate change. And we can see up the top left-hand side, that's the Black Summer year, 2019, which is an outlier on this graph. But as we can see, is if we actually then take these graphs and put on similar ellipses for scenarios for 2030 and 2050, 2019 doesn't look extreme at all. And so we need to be very concerned, I think, about climate change because we know what Black Summer did to animals, we know what it did to humans, we know what it did to our landscape and our economy. So this is a very concerning picture, and you can see very simply from these graphics the degree of change that we're likely to experience and the change in the operating environment in which you're being asked to treat animals under your care. If we look at fire risk, which of course fire is an important feature in Australia, which what happened in Black Summer particularly motivated people when they saw things like the burning animals in that year and the sheer toll those fires had in terms of the native biodiversity. And when we look at what's going on with fire and fire risk, it's already changing quite radically across Australia. So we see the top right-hand corner, that's the fire danger index map, and we can see that the dark red colours where fire danger index is getting worse. We can see that's pretty much most of the continent except for some parts in the centre and northwest, particularly in the southeast, it's going up and up. And of course, this has all sorts of implications like we saw in the Black Summer. If we look at the area burnt, the top left-hand panel is what happens in the standard, what we think of the standard fire season, which is, autumn, late autumn through to, or early spring through to autumn, sorry. And we can see that there's a tendency to a linear increase, although Black Summer was a massive outlier on that. So in the Black Summer fires in Southern Australia, an area around about 6 times the area of Belgium was burnt, to put it in some international context. So we see this expansion of area burnt in our standard fire year, the sort of summer period. We're also seeing an expansion, but an exponential expansion during our off-season, the autumn and winter period, when we tend to see less fire risk. And so we're seeing this exponential increase in area burnt in those cooler periods. And regardless of which metric we look at for fire, it's actually getting worse. So fire season is extended, fire intensity and frequency have got worse, days of higher fire danger have increased, and the affected area has increased, as you can see in those graphs above. And when we look at future projections of climate change, all of this just gets worse and worse over time, even though a lot of those projections, as I would argue in a different presentation, are actually underestimates of the increased risk. If we look at livestock, and this is just one example of that. So if we look at the graphs down the bottom, this is an IPCC, Intergovernmental Panel on Climate Change graph. And this is just an indication of the nature and size and frequency of climate-related shocks to livestock systems. So the top is on cropping systems, and the bottom panel is a map showing where it's really bad, and a graph showing on the right-hand side. And we can see that on that livestock graph, we can see not only are the shocks becoming more frequent, but they're also becoming larger. So those things which provide problems to our livestock systems, which includes both the hot extremes and the wet extremes, are getting worse and worse over time. If we want to avoid this future, we have to reduce our greenhouse gas emissions. Jeff was talking about offsetting those, but we have an even bigger challenge in just simply reducing the amount of fossil fuels we dig up and put into the atmosphere. And now what this graph shows, again, it's an IPCC graph, and it shows the sort of red and orange colors at the top is where we're heading with our currently implemented policies. And this will lead to a world of something like around 3.2 degrees hotter than the pre-industrial average. Now, that mightn't mean a lot to you. Is 3.2 a lot? Is it a little? I can tell you it's a lot. It's absolutely huge when we think about the Earth system. So to put this in context is if we look back at our last ice age, our last glacial period, that was around about 5 degrees colder than our historical temperatures. So 5 degrees gives you an ice age with all of the implications that has, massive kilometers of ice over parts of Europe and North America, for example. Our sea levels were 120 meters below where they currently are. That's what 5 degrees does to the Earth. It's really, really non-trivial. So when we start to think about 3.2 degrees, that's effectively like 2/3 of an ice age, but obviously in reverse. So it's warmer, not colder. So we're not seeing lowering of sea levels, but higher, raising sea levels. We're not seeing, massive amounts of ice over parts of the Northern Hemisphere. We're seeing shrinkage of that ice, and similarly over Antarctica. So even though it mightn't sound much, 3.2 is really, really big. And we can see that the only way we can actually have, instead of heading to those sort of really problematic scenarios, heading towards the temperatures which are enshrined in the Paris Agreement. So that's the 2015 Paris Agreement, which has as a goal, fundamental goals, to limit warming between 1.5 and 2 degrees. The only way we can get to those goals is by a massive reduction in greenhouse gas emissions, in those fossil fuel-based emissions and the other associated emissions. And you can see how far off we are from that trajectory that's consistent with 1.5 or 2 degrees. And so key messages coming out of the IPCC are, if we're to stick to those temperatures and to reduce the potential damaging consequences of climate change, we need very deep, very rapid and sustained cuts in greenhouse gas emissions right across the globe. And so these emissions come from all sectors, so all sectors need to contribute. Now, if we look at what might happen in the future in terms of climate, again, a couple of IPCC graphs. The top left is the change in temperature. Top right is the change in rainfall. Both of these are, if we are looking at a 4-degree world, so that's 4 degrees above pre-industrial, hopefully we won't get quite that high. But we can see the important thing I want to communicate here is not that the temperature goes up, but the temperature goes up differently depending on where you are. So if you're in the middle of a continent, it goes up more than the coastal areas. If you're up towards the Antarctic or down towards the Arctic or the Antarctic, it goes up a lot more than the equatorial regions, and the oceans go up less than the land. So there's no single temperature increase. It depends on where you are. If we look at rainfall, again, even though we expect to see more rainfall on average across the globe as the globing heats up, that's because a hotter globe evaporates more water. The water cycle is accelerated, but the water that goes up into the atmosphere has to fall down somewhere. And so you get increased rainfall, and some places are going to get more of that rainfall, some places are going to get less. So we're going to see changes in distribution of rainfall. And unfortunately, Australia generally is one of those places that's likely to get less rainfall, along with parts of South America, Central America, the Mediterranean, and South Africa. So what we're going to see is a combination of those two things. And you can see, if you try to sort of mentally overlay those two maps, you can see that almost any place will have a different scenario than any other place. So we've got a whole stack of unique evolving climate change scenarios. There is no single evolving scenario which applies to all places. Now, if you just sort of think about what changes in rainfall and temperature and water availability mean to animals and care of those animals, it means that we're likely to see impacts right across the life cycle. So impacts in terms of reproduction, impacts in terms of the growth phase and the maturity of animals as they get more or less vulnerable as they go through their life cycle to climate change factors, and also changes in mortality and morbidity towards the end of life. We're likely to see increased disruptions and damage to animals from extreme events, including fire, heat waves, drought, and storms and cyclones. And we know that people are very concerned when we have extreme events about their pets. So one of the key things when people are being evacuated is the care of their animals. So taking their pets, and in some cases, care of their livestock, being very concerned about how those animals are going to fare in face of those extreme events. We're also going to see changes in various threatening processes, including pests and diseases. So in Europe, for example, we're already seeing expansion of blue tongue viral disease as it moves with warming, as it moves up towards the Scandinavian countries, places where it hasn't been experienced in human history. And we're likely to see increased climate variability and the disruptions that can bring. So think El Nino, La Nina. And so when we look at, in this particular instance, livestock supply chains, and we just break it down into a range of different elements. So, we can see that climate impacts on almost all of these elements. So, for example, climate obviously is going to impact on heat stress. It's going to impact on feed quality, quantity, and variability. It's going to impact on the water and land resources, on production of livestock, on reproduction of livestock, because animals tend not to reproduce as well when it's extremely hot, on diseases, on biodiversity in surrounding areas, and various other things. So almost every part of a livestock supply chain is going to a priori be affected by climate change. So there is no sort of isolation of these things into just one part of the supply chain or one part of the life cycle. It's endemic or systemic across the different components. And sort of delving a little bit into this these are heat stress maps coming from University of Hawaii. If we look at the top left-hand corner, that's our historical frequency of days where temperature and humidity are problematic for animals, animals as well, humans as well as livestock, because we simply can't get rid of the metabolic heat that we produce. So, all of us produce a lot of heat, around about between 60 and 100 watts, depending on how big you are and how rapid your metabolism is. If we didn't get rid of that heat, we'd just burn up, we'd overheat and we'd die. So in a really hot and humid environment, we have trouble getting rid of that heat. So unless we find shelter or reduce our activity levels, our internal temperature goes up with various health implications, which you'd be aware of more than I am. If we actually look at the bottom right-hand panel, that's what might happen to that same metric of heat stress under a high emissions scenario by the end of the century. And we can see, looking at that map, that there's big parts of the world where effectively every day becomes a heat stress day for mammals. And that includes the top end of Australia. Effectively every day will become a heat stress day. So for me, thinking about Northern Australian development without taking into climate change is one of the most bizarre concepts, is that this will become a big implication and barrier, I think, to what we do in the north, both in terms of human and animal activities. If we look at drought, which also seriously impacts on animals and animal welfare in agricultural environments, we're likely to see increases in drought. And so if we look at Australia on this map, particularly the southern half of Australia, very significant increases, but not the only place. So around the Mediterranean, parts of South America, parts of North America, as I indicated before. One of the really important things that's coming out of the science community these days is an emphasis on the need to take into account what we call complex risk. So when we're thinking about animals and how they may suffer under climate change, it's often not a single thing that causes that problem. It's often multiple things that cause that problem. So that's what we call compound risk, where you have risks interacting with each other to cause a problem, or cascading risks, which is where one risk precipitates another risk, which precipitates another risk. So that's cascading risk. Or aggregated risk, which is where two quite different sources of risk can interact. So, for example, when we had cyclones plus COVID, so both are risk items in their own way. But if your response to cyclone was putting people in a shelter where there's hundreds of people in a small place, that interacts with the COVID risk. So you actually get a bigger risk overall than you would separately. And so these types of risk are important to think about when we think about animals. So one example of this, to make this sort of a bit real, is going back a couple of years, we saw this absolutely horrendous event up in North Queensland, where something like 600,000 cattle died in those landscapes. And what happened here was there'd been an extended drought. So this is an El Nino related drought. And so these animals were on very denuded pasture, so there wasn't much feed around, and you can see that in this picture. So they had very low energy reserves in their bodies. And then came a cyclone that came across the coast and dumped a huge amount of rain. And that not only produced floods, but it also cooled those animals. So they're in all of a sudden, a very cold and wet environment. And their energy budget simply couldn't cope. So they just didn't have the energy reserves to survive. That combination of low feed availability driving down their fat stores, etc., and then a sudden shock to the system where they needed that energy in their system to cope. And so you had this absolutely horrendous number of animals dying. And like if people, it really wasn't covered in Australian media to the extent that I think it should be, because this was a major event. Now, in face of all of those sorts of changes, we need to think about adaptation. So how do we change our responses and what we do to look after those animals that are in our care and look after ourselves? So that's what we call adaptation. So adaptation is responding to the changes that we're seeing or that we project in the future. And so we, given those sorts of climate change impacts, we'll need to adapt to maintain ecosystem function and values, maintain the animals and the care of those animals that we have. Unfortunately, when in the IPCC we looked at all of the literature on climate adaptation, we found this sentence, which is in italics. So this is a very summarized sentence, which says, most observed adaptation is fragmented, it's small in scale, it's incremental in nature, in other words, tweaking existing systems. It's very sector specific, so we're not learning cross-sectorally, and it's designed to respond to either current impacts or near-term risks rather than the long-term strategic risks, and it's focused more on planning than implementation. In other words, we're talking about it more than we're actually doing. And so that's a pretty damning indictment of our preparedness, I think, to deal with climate change. And I think it's probably fair to say that that applies also to the veterinary profession as well, where a lot of vets probably aren't clued into climate change and the things that it might have implications for. And one of the other conclusions, which I think was important from this report, was effectively an analysis that says the more that the climate changes, the less effective will be our current set of adaptation responses. So at the same time as the underlying risk is increasing, our ability to manage that risk is decreasing, which is a very worrying thing in its own right. So this is a sort of particular slide that comes from the IPCC again, and it's just sort of looking at some of the different dimensions and considerations in adaptation. And I won't go into this particularly at length. I will just, this was a very human-centric diagram in its origins, so just scrub the humans and put in animals and their carers, so we're still there. But it just sort of compares sort of essentially successful adaptation practices with maladaptive practices, so the good versus the not so good. And it just assesses them against your benefit flows to humans and human systems, to ecosystem services, in terms of equity, in terms of the transformational potential, ways of getting out of our current box that we're locked into, and also in terms of reduced greenhouse gas emissions, because we don't want to have an adaptation response that increases greenhouse gas emissions and makes the underlying problem worse. So there's quite a bit of thinking about these sorts of things that applies in general, but not necessarily very much to the veterinary profession. So there are resources to go to have a look. But just I put it together a quick slide on adaptation, and just to give you a little bit of a feel for some of the things we might want to think about in terms of adaptation for animals and for their carers. So one of the things, obviously, when you're looking at pets, our domesticated animals, if we're to look after them, particularly in extreme events, it's providing shelter so that they have somewhere either warm or cool, depending on the environment, to go to, that they have good quality clean water and it's accessible to them, and adequate and appropriate food for the situation. We do have guidelines for humans in respect to this. So we have sort of, what we think of as appropriate approaches to provision of all of these things for humans. And that is probably a pretty good start if we translated those to animal situations. There's also things that we can potentially advise on or advise against in terms of things like breed selection. So some Samoyed, like in the picture, here is, I think we'd have to think of as increasingly inappropriate in a climate changed Australia. It may still work in Scandinavian countries or Canada, but the poor dogs do have a really serious risk of overheating even more than they currently do. If we're thinking about livestock, exactly the same stories in terms of shelter, water and food, is that people have long understood that giving animals good sort of outcomes in terms of these different components does drive improved productivity. It drives improved animal welfare. It drives increased economic benefits as well. And so things like shelter belts to shelter animals from frost or from heat. Again, we need to be thinking about complex risk when we're talking about livestock. So I talked before about that event with that combination of drought and floods and cyclones before. But similarly, on the hot side, we get packages of events such as drought and heat and fire and smoke that cause problems for animals. So we need to be thinking about how to manage not just single risks, but complex risks. Very much better husbandry is really important in driving better outcomes for our livestock. So that's people paying more attention to their animals, to the needs of their animals, to the health and status of those animals, and finding better ways to look after that over time. And I think we're likely to see an increased focus on sort of broad systems improvement for both extensive and intensive animals. So if we think intensive animals, it's improved housing, air conditioning or cooling in those houses, ensuring that animals have high quality water to access, enough space to cool out and to flap their wings if you're a chook sort of thing, but also manipulating feed at appropriate times. So by manipulating feed and feed content, you can ensure that animals don't overheat. So you can provide, if you're on a high production ration for, say, a feedlot animal, where it looks like it's going to be a really, really hot conditions, heat stress type period, you can actually provide a feed ration that actually generates less metabolic heat, but temporarily less production as well. So there's a whole range of things we can tweak in these systems to make them more animal friendly. Similarly, in terms of biodiversity, we're likely to see really big threats. So we've already seen in Australia the first mammalian extinction to climate change. That was the bramble key malomus. And unfortunately, the projections are for more species to follow due to climate change. So we need to be thinking about habitat integrity and removing threatening processes such as feral animals and pest disease and weed incursions. And of course, we actually, in all of this, we need to look after ourselves. So we need to look after the veterinarians, so have guidelines about managing very hot conditions, and so ensuring that veterinarians don't get exposed to unwanted climate risks. And also, of course, making sure that our veterinary infrastructure, including our buildings and cooling systems, are appropriate for a future climate, which is very different from the past, as I showed you earlier. And the last couple of slides are about greenhouse gas emissions. So Jeff introduced this, talking about offsetting emissions through planting trees, and I think that's part of the picture. And when we look at this particular graph, which comes from our World in Data source, the really important thing here is, say, if you look at the top line, which is beef production and the greenhouse gas emissions per 100 grams of protein, that's what this sort of graph shows. And what that actually shows is that you can actually have beef production, which is really dirty in terms of greenhouse gases. So, it's like, 30 kilos of carbon dioxide equivalent per 100 grams of protein. Or you can have clean beef, which is, something like a third of those emissions for the same amount of protein. So there's a huge difference between production systems in terms of the greenhouse gases per unit product. And a lot of that comes back to husbandry. So on the dirty side, that will actually be a system with very, very poor husbandry, largely extensive, very little shelter, very little looking after the animals. On the low end, it's probably going to be a system which actually has really good animal husbandry, where their needs are being looked after, where the energy balance of the animals is a top priority. And so animals are faring very well in that environment. And so the message here is that husbandry is not just important in terms of the sort of climate impacts, but it can also be really important in terms of the greenhouse gas footprint of different systems. When we look at greenhouse gases, so this is very much the figure was on the agriculture and food production sort of side of the equation. But when we look at pet food is an uncertain source of greenhouse gas emissions, and it's very variable. It differs very strongly between whether you're feeding wet feed or high protein, or meat type products, or dry feed, which can be a lot of cereal products. And the greenhouse gas emissions per unit feed varies by about a factor of 8, depending on whether it's wet and dirty or dry and clean. And it's actually probably a couple of % of our greenhouse gas emissions across the globe are associated with pet feed. So they're actually quite a significant source, but again, very uncertain. So there's no good numbers there. It's just approximations at this point. And lastly, and Jeff raised this, is veterinary practices. So, when you open a sterilized package with a new scalpel or something like that, and it's all disposable, there's a huge amount of greenhouse gases in the production of that, the packaging of it, and the disposing of that. And in the human health sector, when all of those emissions are taken up, and the heating and cooling of buildings and the emissions from ambulances, et cetera, are taken into account, it's something like about 7% of our greenhouse gas emissions across Australia are associated with the human health system. And so the veterinary system, of course, isn't as big as the human health system, but it indicates that it probably is a non-insignificant. It's probably in the small percentage, in integer numbers like 1 or 2%, but I haven't actually looked at the equivalent numbers in veterinary systems because they're not easy to come by. But I think one of the critical things within the human health system is there's been a lot of focus on building infrastructure, which is low greenhouse gas infrastructure. So, for example, we've got zero gas hospitals now in the ACT and also in South Australia. So cutting down massively on the greenhouse gases that the hospital systems generate, because you need gas for sterilising as well as heating, etc. And we also see an increased focus on low-value healthcare in the human system because a lot of healthcare either is not needed or actually doesn't generate significant health benefits, even though it generates significant costs and greenhouse gas emissions embedded in that. So what we're seeing in the health system is a push back and a push down on greenhouse gas emissions in various ways. And I know that the climate care program in the Vets for Climate Action also does that in the veterinarian systems, but I think that's going to become an increasing requirement for businesses across Australia as we go into the sustainability standards accounting and also as consumer expectations change, because people will want their animals to be looked after now, but they'll also want the environment to be looked after as well. So I'll just finish with a little analogy just to perhaps help you remember a few of these sort of different elements that I've talked about. So if you think about climate change as this big train heading your way, you're standing in the middle of the track. You've actually got a few choices you can make here. So one of those choices is you can turn and face the other way and ignore it, in which case the train is going to hit you and it's going to make a mess. That's called climate change denial. We can also stare at that train and just get paralyzed by fear and not knowing what to do. And that's also what we see. We see climate paralysis in some people, and because it's too big and too hard and they don't know what to do. And so again, it's going to hit you and it's going to make a mess. The only way is two ways you can stop the train making a mess is if you step off the train tracks one way or the other. You can step off to the left or you can step off to the right. This is called climate adaptation. And a maladaptive response is if you step off the tracks to your left in the face of an oncoming train and you get hit by that train. So you don't want to do that. You actually want to take adaptive action, which makes a lot of sense. So which way you step off the tracks matters. And the last way you can stop this train making a mess is you can try to get in the driver's seat and you can try to slow the train down by putting on the brakes, or you can try to steer it, if there's an appropriate sort of junction, steer it to a safer place. And those are the two action points, adaptation and emission reduction. And I think the veterinary profession has a role to play in both. So thanks very much. I think we're back on.
Yeah, thanks, Mark. That was a great presentation. There's a couple of questions in the chat, so I might read them out, maybe. So we had a question from Anna. She says, given the severe risks to livestock animal welfare that occur during extreme weather events, as well as the role of livestock farming itself as a driver for climate change and biodiversity loss, do you think that realistically veterinarians should be advocating for reducing the national livestock herd in favour of more sustainable use of resources and food sources, particularly given that we have more capacity for this in Australia compared to countries where many people who rely on livestock are subsistence farmers?
Yeah, it's a really interesting one and quite a challenging one because the increased demand for protein, animal protein, which, whether you like it or not, is actually part of the economic system across the globe. And one of the sort of questions is, if we're not going to be producing it, then other countries who have less effective practices in terms of animal welfare, etc., may actually fill that gap. Now, this is also called the sort of drug dealer's defense. If it's not me, it's someone else. And so there are ethical sort of challenges in terms of taking that position. And so it's not straightforward in terms of those arguments. When we look at sort of, people in countries, and it's noted down the bottom, where people who rely on livestock as subsistence farmers, is that those people in life, rely on that livestock. There's many values for that. It's a drought buffer by having livestock. It's an economic buffer. It's a cultural element, owning livestock. It's important for particular practices, including weddings and festivals. It's a transferable item for bartering. And sometimes it's actually part of other agricultural systems through nutrient cycling. So livestock have many different important sort of roles, and I should say, a fundamental source of micronutrients and protein for poor people in many countries. So in a sense, those people have a very different circumstance from a commercial livestock system in Australia. But nevertheless, I think that the same ideas about looking after those animals apply in those systems as they do in our commercial systems. So there's some things which are different across these different systems, and some things which I think arguably similar, where we should be aiming to improve the outcomes. So again, I don't think this is an easy topic, and sort of hardline stances, get rid of meat from systems, don't necessarily pick up a lot of that nuance, which I think we need to have to actually get to good outcomes.
Thank you. There's a question here from Janet, who says, thank you, Professor Howden. When I heard you talking a couple of years ago, you said the government were not interested in listening to climate scientists. Is the current government inviting you to talk to them?
Yeah, thanks, Janet. It is better, and I think we see a lot of more openness to conversations from government. So that's from the politicians, from the political advisors, and also from the public service. So there's a much closer relationship, I think, reasserting itself, because I think the last decade was to some extent an aberration from the long term. And so I think it has improved, but there's probably still some way to go, because clearly the government's taking a whole series of decisions which aren't really well aligned, unfortunately, with our Paris agreements and with the overall outcomes in terms of climate change. And so I think, as always, science and research only has a limited say within the decisions of government.
Thanks, Mark. And then we had a question from the vet students at Murdoch, who asked, you'd mentioned that human hospitals, a couple of them, have become carbon neutral. Do you know how this has been achieved?
Yeah, so not so much carbon neutral, but just zero gas is what I think I emphasised. So these are, in jurisdictions where renewable electricity is now a big part of the picture. So in the ACT, we're already 100% renewable electricity. In South Australia, it's heading towards that way, and some days it's completely 100% renewables. And in that environment, if you've swapped from like a gas heater or a gas sterilizer to an electric one, then you effectively are doing that job. It's the job we want, sterilizing your instruments or whatever it might be. But we're doing that with effectively a zero greenhouse gas footprint. And I think that's a really positive thing, where we can actually say that we're getting the service we want, but with a much, much lower greenhouse gas footprint. Because after all, that's what we want. We don't drive our cars to produce greenhouse gases. We drive our cars to get from A to B or to carry stuff from A to B. Greenhouse gases are just an unfortunate consequence of the technologies that we've got embedded in our system. So, and that's the same with hospitals. We've got a whole stack of technologies which are embedded in our system to deliver specific services. We can find much, much better ways of delivering those services with a much, much lower greenhouse gas footprint. And that's the exploration we need to do. And that's the reason why I think, yes, we can offset our emissions. That's a good thing. We can reduce our greenhouse gas emissions through things like, going zero gas. But we also can push up to the supply chains and saying, we want products which have a much better, lower greenhouse gas footprint or meet other sustainability criteria. So I think there's multiple points where we can actually put pressure on. And the way that was done in the ACT, so my understanding is the initial quotes for that hospital, it's called the Spire extension, were way beyond, to go zero gas, were really big. There was a big premium initially to go off gas and onto electricity. And then the ACT government engineers and others worked with, with the plans, and progressively they identified ways to actually do the things that used to be done by gas, but done by electricity. And so in the end, as I understand it, the premium for going zero gas was around 3%, like it was almost lost in the noise. And there's this massive, massive operating benefit from going off gas, which is really expensive, and going on to electricity, which is relatively cheap. So in the end, it's a no-brainer financially, as long as you work very well to actually get that initial capital cost down. And the reason why it's often inflated initially is because in Australia, we're just not used to, our engineers, our architects aren't used to dealing with, renewable-based appliances and electric-based appliances versus gas ones. So you still see, development companies putting in gas heaters into buildings because that's the way they've always done it. They know the size of the rooms, they know the size of the pipes. It's cheaper, capital cost-wise. And so they go for that. They go for the, the low initial cost, but the long-term big cost.
All right, thanks, Mark. We do have a few more, so we'll press on for 5 minutes if everyone's happy to hang around. Jeremy asks, do you think the current La Nina has reduced the driver for action on climate change? So, and if so, do we have to wait for another El Nino to get more action? How do we make the action more continuous?
People, there's a well-known thing in the drought literature, which is called the hydrological cycle, which is essentially, when it rains, people ignore drought and they forget about it. It's only when you get into drought that people start to get concerned, and then they start to complain to the politicians and try to get some money. By the time the money flows, the drought's broken and people ignore the drought again. And so you never get the sort of progress that's needed. And so I think there is an element of that within the sort of broader community, that some of the pressure which was in that Black Summer period has been taken off because it's just much less present, and there's always other problems to focus on. Having said that, is that when we look at the levels of interest in climate change and the demand for more action on climate change, in surveys, that does not change. So in spite of the 3 years of La Nina, we saw a consistent desire for increased action on climate change across the Australian population. So even though that may not have been quite so urgent, people were still sticking with that as a strategic view.
Great, thanks, Mark. We had a question from Michael, who says, at +4 degrees, your graph suggested that rainfall across Saharan Africa, the Middle East, and India would increase by 30 to 40%. Is this likely to offset mass movements of displaced people?
Well, the problem with Sahara is a big increase of almost nothing is still almost nothing, and so your your evaporation in that environment is so much bigger than your rainfall. Yes, a bit of extra rainfall on average is not a bad thing, but it's actually not going to fundamentally change it from being a desert. There are other things you can do at the margins to improve the situation there, including, regreening situations, regreening landscapes, but that happens usually where there's more rainfall. So important just to separate out the relative increase from the absolute increase and the implications of that.
Janet had another question. We'll just maybe ask two more and then we'll wrap up. Janet asks, what more can climate action groups do to encourage the government to take actions that are aligned with climate science?
I think just speak out to governments, so push up into the governments, push up into industry. So governments listen to industry, it seems, a lot more than they listen to the citizens, except around the election time. So push up into industry, and where industry either has the threat of removal of social license or the possibility of increased profits, they will move and they will lobby governments to enact action on their behalf. And so, it's not just about governments, but it's also about industry. And also, I think, just communicate with members of the general public, as you're already doing, to emphasize the importance of climate change on the things that they find are really important, and to encourage people to talk to other people and to get informed.
Cool. All right, we'll do last question, big question from Jen. As someone looking at the science day to day, how optimistic or otherwise do you personally feel?
Yeah, so I guess there's a personality thing, so glass half full, glass half empty sort of people, and so I tend to start off on the optimistic side anyway. Look, I think the cold hard analysis is that we're not going to meet 1.5 degrees. I mean, it's not impossible that we would meet it, but it's highly unlikely at this point. We are going to have to deal with very significant climate changes, and that will have big impacts on the things that we value, including on animals and their welfare. But some of those impacts are manageable, but some of them aren't. And we need to be very aware and clear-eyed about that that's the case. We're not going to be able to remove all of the risk, no matter how good risk managers we become. So my sort of perspective is I'm hopeful that we will take effective action, but I'm disappointed that that action won't be big enough and fast enough to actually avoid a lot of costs to humans, animals, and the environment more broadly.
All right, we might leave it there for the questions. Thank you everyone for your excellent questions tonight. And thank you, Mark, for joining us. That was very informative, super interesting, and really kind of brings back how we can, like why we need to act and how we can apply this. So it's really fantastic. So thank you very much for talking to us. Much appreciated giving up your evening. For anyone who doesn't know enough about VetCA Climate Action, please get online and have a look at our website. Our climate care program is up and running with a bunch of clinics joining again this year, so definitely have a look at that. And I'm a volunteer, and you can volunteer too. So if you're interested in getting involved, please jump online and get involved. It's really rewarding. Even with the tech struggles. So thanks everyone for joining us tonight. Just a reminder that VetCA Climate Action does run on donations, and now is a great time to donate because it's the end of the financial year. So Jeanette, the VetCA Climate Action Chair, is online with us, and she's happy to hang around and have a bit of a chat if anyone wants to have a chat with her. I'll turn off the recording, but keep the room open. So feel free to stay in and turn yourselves off mute and chat. Once again, Mark, thanks for joining us. Thanks everyone for tuning in, and we'll see you at the next webinar.